previous lecture, we had started a discussion of particle in a box problem. We considered a particle in a three-dimensional box of volume L cubed and obtained the energy states of that. However, before that we had discussed the corresponding one-dimensional problem, and I thought today we will start our discussion on showing the actual wave functions corresponding to a particle in a one-dimensional potential well. So, this is the software that we have developed, and if you could show the laptop, then we consider a proton of mass 1836, the electron mass, and the potential depth is 25 MeV, and as we had discussed earlier, we assume that the width of the potential well is 3.65 Fermi, that is 3.65 into 10 to the power of minus 15 MeV. For this, the value of alpha we had found to be 2.0, and we had obtained two discrete eigenfunctions. So, this is the potential well, and the first eigenfunction has a value of 6.62 MeV, and it is a symmetric state. The second eigenfunction has energy eigenvalue of 22.44 right at the edge of the potential well, and it will be an antisymmetric eigenfunction. Now, let me make this 2 times this value, so that instead of 3.65 we write 7.30 Fermi. So, that the width of the potential well has now increased. Now, we have 3 eigenstates. The same potential well with a width which is now 3 Fermi will have 3 eigenstates. The ground state will have will be symmetric function of x, which has an energy eigenvalue of 2.45 MeV, and the second one will have a eigenvalue of 9.55, which is an antisymmetric function of x, and the third eigenstate will have the energy which is 20.17, and again it is symmetric. Now, if I make the value of A twice of this, so that instead of 7.3 Fermi, if I made 14.6 Fermi, so that the width of the potential well has been made double. Let us solve this. Now, we have 6 discrete eigenvalues, and the first eigenvalue, which is the ground state, which has an eigenvalue of 0.76 MeV, is a symmetric function of x, and it is more confined within the potential well. The second one will be has an eigenvalue of 3.02, which is antisymmetric. Inside the well it is a sine function, and outside the well it is an exponentially decaying function. Similarly, the third eigenstate will have an energy 6.77 MeV, which will be symmetric. Inside the well it is a cosine function, outside it is an exponential function, outside it is and it is symmetric about the center point, because the potential is also a symmetric function of x. So, the fourth eigenfunction, the energy eigenvalue is 11.9 MeV, and it is an antisymmetric function of x. That is, inside the well you have a sine function, and outside the well it is an exponentially decaying function. Similarly, fifth eigenvalue is 18.2 mF, and it is a symmetric function, and finally, the sixth eigenfunction is an antisymmetric function of x. It is exponentially decaying here and exponentially decaying here, and inside the core we have 6 eigenfunctions. So, this is the software that we had developed. I had shown you earlier. This is the basic quantum mechanics, a book on basic quantum mechanics, in which we have developed a software to understand basic simple problems in quantum mechanics. So, this is how a square well potential looks like. If I had solved a double well problem, then the wave functions would be like this. This double well problem is also a symmetric function of x. So, the wave functions are either symmetric or anti-symmetric. So, the first wave function is like that, and the second wave function is like that, and so on. And the software allows you to calculate the eigenvalues for a multiple well problem. But that is slightly complicated, because we have to develop a numerical method for solving the Schrodinger equation. It is possible to do that. It is not very straightforward, but it will take some time. Maybe at the end of the course we can discuss that. Before we go to the particle in a box problem, let me consider the single step barrier, and let me assume that the step is 10 MeV. The mass of the particle is 1836 times the mass of the electron, which is the mass of the proton, and it experiences a potential step of 10 MeV. So, this is the reflection and the transmission coefficient. So, you have here the incident energy. Incident energy is 0.5, the reflection coefficient is 1, there is a total reflection. So, this is the incident wave, this is the reflected wave, and then there is an evanescent wave here. The reflection is complete. So, this is what so a particle is incident from the left on a potential step, which is of height 10 MeV, and it is a proton that we are assuming, and we consider an energy of the proton which is half of this value, which is 5 MeV. 5 MeV. If we make it more than 10 MeV, let us suppose E by V becomes 2.0, then we will find that there is an incident wave here, there is a transmitted wave here, and then there is a reflected wave here. So, the reflection coefficient is about 0.03, and that is about 3% reflection, and the transmission coefficient is 97%. The 97%. So, you can see that that the amplitude of the wave is slightly larger here, and that is a consequence of the fact that we have to calculate, we have to be careful in calculating the transmission coefficient. We have to consider the currents and not just the amplitudes. So, the R plus T, the reflection plus the transmission coefficient, must be equal to unity. So, this is what the single step looks like. Then we considered a single barrier, and so you have an incident wave here and a reflected wave here and a transmitted wave here. So, let me make this as 10 MeV. This is a proton, and this is the reflection coefficient and the transmission coefficient, and so this is the incident wave, this is the reflected wave, and this is the transmitted wave. And you can go to multiple barrier problems also, very straightforward. We consider these are the reflection and transmission coefficient. Any particular potential energy variation can be used, can be put into the software to calculate the reflection and the transmission coefficient. You have here we have two potential bumps. You can have 3, 4 or any number, and you can use the software to calculate the reflection and transmission coefficients for a single barrier or a multiple barrier or for any potential energy distribution that one can think of. So, so this sort of completes the analysis of potential step and potential barrier, and also the potential well problem that we had discussed in our previous lecture. We continue our discussion on for a particle in a box, and we will calculate the density of states for such a problem. We had in the previous lecture we had considered the solution of the Schrodinger equation del square psi plus 2 mu by h cross square E minus V of x. The potential energy function is 0 inside the box. We considered a box which is of length L, height L and width L. So, that this is the box that we had considered, and this is an infinitely deep potential well. So, the wave function was vanished at each point on the surface, and we obtained the following E was equal to, the energy eigenvalues was equal to h cross square by 2 mu k x square plus k y square plus k z square, and we had obtained h cross square by 2 mu n x pi by L whole square plus n y pi by L whole square plus n z pi by L whole square. So, these are the discrete eigenvalues of the problem. So, you can take the pi square L square inside. So, you have pi square h cross square by 2 mu L square n x square plus n y square plus n z square. And as we had discussed in the previous class, these can take any integers. N x is equal to 1, 2, 3, 4, similarly n y and similarly n z. They will not, a negative value will not lead to any new state, it will not lead to a new wave function. That is because that the corresponding wave functions are given by, the normalized wave functions are given by x, y, z, 2 by L, this is the normalization factor as you know, 3 by 2, then sine of n x pi by L, sine of n y pi by L times x times y times n z pi over L into z. These are the rigorously correct wave functions, normalized wave functions correspond. So, of course, 0 less than x comma y comma z less than L, the wave function is non-zero only inside the box, and of course, n x, n y, n z takes the values 1, 2, 3, 4, 5 integers. If I take the value 0, then of course, this whole wave function becomes 0. So, that is the trivial solution. So, n x, n y, n z equal to 0, that corresponds to a trivial solution. And also, if I take say n y equal to minus 2, then if I take plus 2 and minus 2, it will only change the sign of the wave function, to which the wave function is always arbitrary. So, it will not lead to any new energy state or a new wave function. So, that we restrict ourselves to only positive integers value, integral values of n x, n y, n z. Now, as we had mentioned in the previous slide, the energy eigenvalues are pi square h cross square by 2 mu L square, n x square plus n y square plus n z square. Now, as you know, h cross is a constant. For a given box, L is a constant, mu is the mass of the particle, that is a constant. Now, I want to find out the total number of energy states whose energy is less than E. So, therefore, I rewrite the above equation like this: n x square plus n y square plus n z square is equal to 2 mu L square E by pi square h cross square. So, let us suppose I put E equal to say 10 MeV. Then for given values of mu, L, h cross, this right hand side is a number, is a dimensionless number. And so, therefore, if I assume say E is equal to 10 MeV, then the right hand side becomes a number. Let us suppose it is a number like say 10 to the power of 6, some number. Then I have to find the sets of integers such that the sum of their squares is less than 10 to the power of 6. So, there is a very easy geometric method to do that. So, let me restate the problem. The problem is I want to find out the total number of states whose energy is less than E. I take a fixed value of E, say 10 MeV, and I substitute in this expression and find the right hand side. I know the particle, which in this case will be electron. So, I know the electron mass. Let us suppose it is 1 meter by 1 meter by 1 meter, or 1 centimeter by 1 centimeter by 1 centimeter. So, I know what is L and what is H cross, and if I specify the value of E, then the right hand side is a number. Let that number be 1 million, let us suppose. So, I want to find the sets of integers such that the sum of their squares will be less than 10 to the power of 6. So, you can see nx can be 1, 2, 3, 4, 6, so on, ny can be a large number of numbers, and nz will be a large number of numbers. Of course, none of the integers will be more than 10 to the power of 3, that is the largest value of either nx, ny or nz will be less than 1000, because if it is 1000, then that number itself, the square of that will become 10 to the power of 6. Now, let me tell you the method of calculation, and before that let me do a simpler 2-dimensional problem, and that is, let me consider the total number of sets of integers such that the sum of their squares is less than r square. Now, in order to understand this, I have drawn a graph paper, and you see each corner on this is an integer. This is 1 1, this is 2 2, this point is 1 2, this point is 1 3. So, I want to calculate this radius that I have drawn is of radius 17 units. So, 1 2 3 10 11 12 to 17. So, I want to find out the sets of integers such that nx square plus ny square is less than 17 square, and this, as we all know, is 289. So, on this graph paper I draw the quadrant of a circle, because nx and ny take only positive integers, and each point on this graph paper is associated with a particular set of values nx and ny. For example, here this is 5 comma 5 or 6 comma 5, this is 7 comma 8 or something like that. So, any point inside this will be such that their sum of the squares will be less than, because this is the radius of the circle. Any point outside, for example, here this is 15 here and 15 here. So, for this is 15 and 15. So, this the sum of the squares will exceed 289. So, therefore, if I want to find out the sets of integers whose sum of squares is less than 289, then it will be the number of points number of corners that are there with and with each point I can associate a unit area, so that the total number of states such that the value of nx square plus ny square is less than 289 will be the area of this quadrant of the circle, which is pi r square by 4. So, therefore, in this particular case the area of the circle is pi r square, and since we are considering the fourth of the, because we are restricting ourselves nx and ny positive. So, in this case it will be pi into r square, which is 289 divided by 4, and I think the approximate value is 220. It will come out to be not an integer, but these are approximate calculations. So, therefore, each corner, each point on this matrix, on this grid, corresponds to an eigenstate, correspond to an integer value of nx and ny, and so therefore, with each point is associated with an unit area here, and so therefore, the number of points in this quadrant will be approximately equal to the area of the quadrant when this value of r is very large, and so therefore, the total number of states will be approximately equal to pi r square by 4. Now, so this was the case. So if I want to find out the sets of integers such that I want to find out nx square plus ny square is less than r square, then I have to draw a quadrant of a circle of radius r, and the number of sets of integers will be equal to pi r square by 4. But our problem is slightly more complicated, because now I have sets of 3 integers, nx square plus ny square plus nz square is equal to r square. So, I want to find out the sets of integers such that their sum of the squares is less than or equal to r square. So, I have to take a 3-dimensional plane. So, nx, ny and nx, ny and nz, and each point on this we draw small cubes here, and each corner will be a point will correspond to an integer value of nx, ny and nz. So, that the total number of states for which nx square plus ny square plus nz square is less than r square, now it will be the volume of the cube, the octant 1/8, because we are only considering positive values of nx, ny and nz. Here we had pi r square by 4, but it has 8 octants in a 3-dimensional geometry. So, the total number of states will be equal to 1/8, that is the octant, multiplied by the volume of the sphere, that is 4 pi by 3 into r cubed. Now, if you recollect that we had nx square plus ny square plus nz square, this is equal to 2 mu L square E by pi square h cross square. So, this was my r. So, the total number of states, so 4, this is 2. So, n of E will become pi by 6 into r cubed, that is 2 mu E by pi square h cross square raised to the power of this is r square, this is r square. So, this will be raised to the power of 3 by 2. And in each state, if I am considering electrons, you can have spin up and spin down. So, that the number of available states for the electron will be 2 times this. So, this will be the total number of states whose energy is less than E. So, this becomes equal to, if I simplify this, pi over 3 2 mu raised to the power of 3 by 2 divided by pi cubed h cross cubed times e to the power of 3 by 2. So, therefore, we obtain that the total number of states, this is total number of states whose energy is less than E is approximately 1 pi cancels out with pi cubed, and so you will have 2 mu raised to the power of 3 by 2 divided by 3 pi square h cross cubed into e raised to the power of 3 by 2. So, this is the total number of states whose energy would be less than E, and we have taken into account the fact that each state can be occupied by 2 electrons, spin up and spin down. So, this is the total number of states whose energy would be less than E. Now, last time we had shown that the density of states, total numbers density of states is defined like this: G of dE is the number of states whose energy lies between E and E plus dE. And then we had shown that the density of states will be equal to dN by dE. So, that is a very straightforward differentiation. So, that will become 3 by 2. So, this will become 3 will cancel out, 2 pi square h cross cubed multiplied by 2 mu raised to the power of 3 by 2 e to the power of half. This is an extremely important formula for density of states, which is extensively used in solid state physics and in many other areas. And this density of states is such that that G of E is proportional to e to the power of half. Now, let me apply this concept to the case of electrons. As we know that in sodium, we consider a sodium metal. Now, inside that metal, associated with each sodium atom, there is an electron which is almost free. So, therefore, we can assume that with each atom there is a free electron which is free to move inside the metal, but it cannot escape from the metal. So, it is actually inside a 3-dimensional box that we are being considered. So, let us suppose I am sure you are familiar with what is known as the Fermi Dirac distribution. The Fermi Dirac distribution, which is usually represented by the symbol capital F, is a function of temperature and is the probability of occupation of a particular state. And this function is given by 1 plus e to the power of E minus E f by k T. If at temperature at T at absolute 0, if E is greater than E f, then this is positive. So, it is e to the power of T is extremely small. So, it is e to the power of plus infinity. So, f of E is 0 for E less than E f 0. This is known as the Fermi energy, and the Fermi energy is a function of the temperature. So, at absolute 0, sorry, I am sorry, this is E greater than E f 0, I am sorry. So, because when E is greater than E f, this quantity becomes positive. So, this is e to the power of infinity, e to the power of infinity is infinity. So, 1 over infinity is 0. On the other hand, for E less than E f 0, E less than E f 0, so this quantity is negative. So, it is e to the power of minus infinity. If it is e to the power of minus infinity, then this is 0. So, f of E, this quantity is 0. So, this is 1 over 1. So, at 1. So, therefore, at absolute 0, all the states below the Fermi energy are occupied, and all the states above the Fermi energy are unoccupied. The probability of occupation is 0, and for all energy states for which the energy is less than E f 0, the probability of occupation is 1. So, let me calculate the total number of electrons inside a metal. Unfortunately, we are using the same symbol n, which is the total number of electrons inside a metal. So, this will be equal to the density of states multiplied by the probability of occupation of the state. So, this is the probability of occupation of the state multiplied by G of E d E, and from 0 to infinity. This is a rigorously correct expression. At absolute 0, we find that all the states f of E is 1 for less than E f 0. So, E f 0, and beyond that it is 0. So, this will become G of E d E, and so therefore, you will obtain, if I substitute the value of G of E, so this will become 2 mu raised to the power of 3 by 2 divided by 2 pi square h cross cubed e to the power of half d E. So, 0 to E f 0. This is a very trivial integral. The integration is 2 by 3 e to the power of 3 by 2 evaluated between 0 and E f 0. So, this will become 2 by 3 E f 0 raised to the power of 3 by 2. So, this 2 this will come here. So, this 2 will cancel out with this 2, and we will therefore obtain that the expression that 2 mu raised to the power of 3 by 2 divided by pi square h cross cubed multiplied by 3 E f 0 raised to the power of 3 by 2. I am sorry, for this multiplied by, there is a factor which is L cubed, which I have missed. I am sorry. So, even here you may correct that there is a factor which is multiplied by the volume of the box. So, I am sorry, there is an L square factor here. So, when you take the 3 by 2 factor of that, so there is an L cube factor here. So, L cubed is the volume of the box which is present everywhere. So, this factor I have missed. So, you have here is a factor V, where V is equal to L cubed. So, I can either write L cubed or I can write V. So, here you have multiplied by V. So, let me write this down once again. So, the total number of electrons inside the metal will be 2 mu raised to the power of 3 by 2 divided by 3 pi square h cross cube multiplied by V. So, let me rewrite this. So, you have here n is equal to 2 mu E f 0 raised to the power of 3 by 2 divided by 3 pi square h cross cubed, and there is a volume here. So, I put the volume here. So, this is the total number of electrons in volume V. So, this is the electron density, number of electrons per centimeter cubed. So, from this we can write down 2 mu E f 0 is equal to 3 n pi square h cross cubed raised to the power of 2 by 3. So, this is the final result for the so, we will get E f 0 becomes h cross square by 2 mu multiplied by 3 pi square n raised to the power of 2 by 3. Now, if I consider this is the expression for the Fermi energy of the electron at absolute 0. Now, let me consider the sodium metal example. Let me consider sodium metal. Sodium, it has a density of 0.97. Actually, I am using grams per centimeter cube, and if I use the Avogadro's number, then the total number of electrons, if I assume 1 electron per atom, and then there are 6.023 into 10 to the power of 23 atoms for 23 grams. This is the atomic weight multiplied by the density. Then you will get approximately 2.54 into 10 to the power of 22 electrons per centimeter cubed. We are using here the CGS system of units. So, once again I consider sodium metal, which has a density of 0.97 grams per centimeter cube. 23 grams of sodium will have 6.023 into 10 to the power of 23 atoms. Each atom will have 1 electron. So, that 23 grams will contain 23 grams of sodium will contain 6.023 into 10 to the power of 23 electrons, and since the density of sodium is 0.97 grams per centimeter cube, the number of electrons per unit volume will be equal to this number divided by 23. So, if you carry out the calculations, then it comes out to be 2.54 into 10 to the power of 22 electrons per centimeter cube. Now, if you substitute this number in this expression, and you know the value of h cross, you know the value of mass. So, this comes out and you transform into electron volts, this will come out to be 3.2 electron volts. So, this is the Fermi energy at absolute 0, Now, the average energy is given by the 0 to infinity E g of E f of E dE divided by 0 to infinity g of E f of E dE. We have calculated this for at absolute 0. If I calculate this at a particular temperature, the calculations are slightly cumbersome, but the final result is average energy is 3 by 5 E f naught, approximately equal to 1 plus 5 pi square by 12 kT by E f 0 whole square plus so on. So, usually at room temperature, for example, T equal to 300 degrees Kelvin, kT is about equal to 1/40th of an electron volt. And we have just now seen that EF naught for sodium is about 3.2 electron volts. So, EF naught is much greater than kT. And so, therefore, although the sodium metal is at 300 degrees Kelvin, but we can assume that almost all the situation is somewhat similar that exists at 0 degrees Kelvin, and we say that it is in an almost degenerate state. That is, all the levels up to EF0 are filled up, and beyond EF0 all the states are empty. Using this expression for the average energy at T equal to 0, at absolute 0, the average energy is equal to 3/5 EF0. And since kT by EF0 is usually a very small number for normal temperatures, so therefore, this correction term is very small, is usually very small. And using this expression, we can calculate the electronic specific heat, and we will find that the electronic specific heat, I leave this as an exercise, will come out to be pi square n, the total number, n0, which is the Avogadro's number, k square T divided by 2 times F0. And if I consider this to be a free gas, then the specific heat comes out to be at constant volume 3/2 kT, 3/2 N0 K. So, this specific heat is extremely small, and this is a consequence of the fact that you see at absolute 0, the Fermi function is something like this. This is EF0, this is the Fermi function f of E, and you have all the states filled up below EF0 and all the states are empty above. At room temperature, for example, in sodium, it will be something like this. So, only a small number of states around this EF0 will have a slightly lesser probability, and only these electrons will go here when you heat it up. So, these electrons really do not contribute to the specific heat, and so therefore, the electronic contribution to this specific heat is much less than what we would expect from the classical from if we had assumed that the electron behaves like a classical gas. Even the electrons in white dwarfs can be approximately assumed to be free and in a completely degenerate state, and that leads to the theory of white dwarf stars, which is quite easy to understand once we have understood this the free electron theory from the particle in a box problem. So, that we conclude this part, this solution, we considered the solution of the Schrodinger equation, the solution of the 3-dimensional Schrodinger equation for an electron confined in a box. We found the energy levels, and from the expression for the energy levels, we calculated the density of states, and then the expression for the total number of electrons inside the box, and we applied it to the sodium metal, and if we assume that there is only one electron per atom, then we calculated the Fermi energy at absolute 0. Since the Fermi energy at absolute 0 is much greater than kT, we found that EF0 was about 3.2 electron volts, and at normal temperature KT is about say 1/40th of an electron volt. So, EF0 is much greater than KT, and therefore, we say that at normal temperatures, at not too high temperatures, the electrons inside the metal is in an almost completely degenerate state. And what we imply is that as far as the Fermi function goes, we can assume the temperature to be absolute 0, and we say all the states below EF0 are filled up and all the states above EF0 are empty. So, that concludes one section of the course, namely the solution of the Schrodinger equation for typical one dimensional, and in the last case in the 3 dimension also the solution of the Schrodinger equation for the particle in a box problem. Our next topic of discussion is the angular momentum problem. So, we continue our discussion on the angular momentum problem. Now, how do we start this? In classical mechanics, the angular momentum of a particle, as you all know, is defined by this following vector relation: L is equal to r cross p, where r is the position vector and p is the momentum vector. So, if I take, as you all know, Lx will be y p z minus z p y, similarly Ly, and similarly Lz. Lz will be x p y minus y p x, z p x minus x p z. They are in cyclic order: y z x, z x y, z x y, y z x. So, they are in an x y z. So, they are all in cyclic order. So, these are the definitions of the x, y and z components of the angular momentum in classical mechanics. We take over the same definitions in quantum mechanics, except now that we consider the operator representations of Px, Py and Pz. That is, we replace Px by minus IH cross delta by delta x and Py by minus IH cross delta by delta y, and Pz replaced by minus IH cross delta by delta z. So, they are now considered as operators. For example, Lz will become equal to minus IH cross x. So, Lz operating on a wave function will become x delta by delta y psi minus y delta psi by delta x. So, this is the operator representation, and it will lead to very important consequences, as we will just now show. However, to discuss further properties of the angular momentum operators, it is necessary to introduce the spherical polar coordinates. I am sure all of you are familiar with spherical polar coordinates, and in this system of coordinates, a point P, as you all know, is represented, for example, as x, y, z and also as r theta phi. If this is the origin, then this is the point P, then this distance is r, this is the z axis, this angle, this is known as the polar angle, this is theta, and this is my x axis and this is the y axis. So, I drop a perpendicular on the xy plane, and this angle is denoted by phi. So, therefore, on the xy plane, this length is equal to, therefore, the z coordinate, the z will be equal to, the z is equal to r cos theta, and if I drop the perpendicular here, this length will be r sin theta. So, you have here the x and y axis, x and y axis, and this distance is r sin theta, and this angle is phi, and therefore, this distance is r sin theta cos phi, x is equal to r sin theta cos phi, and y is equal to r sin theta sin phi. Because if you drop a perpendicular from here, then this distance is equal to r sin theta sin phi. So, once again, if I have any point P here, and therefore, if the distance here is r, this is the azimuth angle, this is theta, and so therefore, this distance is r cos theta. Then I drop a perpendicular on the xy plane, this is my x axis and this is the y axis. This angle is phi and this side is r sin theta. So, the x coordinate is r sin theta cos phi and the y coordinate is r sin theta sin phi. Now, we will represent the angular momentum operators in spherical polar coordinates. So, using this, so let me rewrite this. So, you have x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. If you square and add them, then you will obtain x square plus y square plus z square. Please see this, x square plus y square will be r square sin square theta, because cos square phi plus sin square phi will become 1. So, r square sin square theta plus r square cos square theta, that will be just r square. And the second will be that if I divide this, so you will be having y by x will be tan phi, y by x will be tan phi, and then x square plus y square by z square. This will be r square sin square theta by r square cos square theta. So, that will be equal to tan square theta. So, these are the three relations that relate the spherical, these are the 6 relations from which relate the Cartesian coordinates with the spherical polar coordinates. For example, here if I differentiate partially with respect to x, I will get 2r delta r by delta x is equal to 2x. So, therefore, delta r by delta x will be equal to x by r, and here this is r sin theta cos phi. So, this is just sin theta cos phi. So, we will continue our discussion from this point onwards. Thank you.